The diagram shows a light spring of natural length 0.4 meters and modulus of elasticity 1470 newtons, with one end A fixed and the other end attached to an object P of mass 15 kilograms. Initially, P hangs in an equilibrium with the spring vertical. A. Determine the extension in the spring. Well, let's use the diagram to help me in this question. What I know is we have this scenario. Let's say the natural length is around there. So the natural length is 0.4 meters. I've got an extension of x. I don't know what that extension is. I know that we've got a mass acting here of 15g and that there is a tension acting upwards. Let's call that T. Now, starting the question, if I resolve upwards to find that tension in the string, what we have is T minus 15g equals 0. So T is equal to 15g. Now if we use T equals lambda x over A, the natural length, then we can have 15g equals 1470 times x over 0.4, not 0.8. So if I times by 0.4 and I divide by 1470, what we're going to get is that x equals 0.04 meters. Okay, just 3 marks for this question. What do we get the 3 marks for? Well, first of all, standalone mark if we have resolved to get that T equals 15g. Next, using Hooke's law, we get the method mark, and finally get an extension of 0.04 meters. Correct answer only. In whatever format, we get a final accuracy mark. Okay, let's look at part B of this question. It says the object P is pulled downwards so that the total length of the spring is 0.56 meters, is then released. It says calculate the speed of P when it is at a distance 0.45 meters from A. So this question bears no relation really to the initial question at all, other than the fact we're using the same spring. So what we have, if I draw a diagram, just a nice bit of space, is I have this situation where here's my particle of mass 15g. I have a tension acting upwards. What we have is we have the natural length, which is 0.4, and x equal to an extension of 0.16. And what I'm going to do is I'm going to take this level here as the potential energy equals 0, since it's the lowest point of the system. And then we have this other scenario. Let's call this scenario A. Have this other scenario. Still got the 15g. Still got a tension. However, this time the particle is going to be moving. Now, what we know is this time, the distance between the two, there is the 0.4 natural length, but it's 0.45 away, so we have an extension x equals 0.05. And so that means if I wanted to measure this distance here, because I'm going to be using this for potential energy in a moment, the height is 0.11 meters. Okay, so working through this, if we call this scenario B, let's consider energy at A, or at the start. What I know is it's being held at rest, so the kinetic energy is 0. And I know since I've set the potential energy to be the lowest point, potential energy is 0. So all I have is elastic potential energy, lambda x squared over 2a. which is going to be 1,470 times 0.16 squared all over 2 lots of 0.4. And the elastic potential energy here comes out as 47.04 joules. So at the start of the question, start of the scenario, the particle has energy, or the system has energy 47.04 joules. Now, at point B, there is potential energy. So let's do potential energy, which equals mass times gravity times height. So we get the potential energy equals mass, which is 15 kilograms, times gravity, which is 9.8, times the height, which we calculated the difference between the two heights, 0.11. And by taking the potential energy at the bottom of the system, we get all positive energies. And when we work through this potential energy, we get a potential energy of 16.17 joules. Now, additionally, at this point, the particle has elastic potential energy because it has an extension of 0.05. So the elastic potential energy is going to be equal to lambda, which is 1470, times the extension squared all over 2 times the natural length, which is 2 times 0.4. And when we calculate the elastic potential energy here, we get 4.59375 joules. Finally, at B, we have kinetic energy. However, kinetic energy equals a half mv squared. We're going to do a half times 15, which is 7.5, and we don't know the v. The whole point of the question is I'm looking to find the velocity or the speed of that object at that point. Now, I know all the energy at the start of the system. I know all the energy at the end of the system. No other forces have been applied to the system, so we can apply conservation of energy to this scenario. I'll put B on the left-hand side, so we've got 7.5 v squared plus 16.17 plus 4.59375 is equal to 47.04. So the energy at B is equal to the energy at A. Let's subtract the 16.17 and subtract the 4.59375 from both sides, so that I get that 7.5 v squared is going to be equal to, and let's double check this quickly, so we've got 47.04 minus 16.17 minus 4.59375. What we get is, let's just call this 26.28 for the times being. Let's divide by 7.5. So now we get v squared is equal to 3.5035, and then if we take the square root of both sides, we get that the velocity is 1.87 meters a sec to 2 decimal places. Okay, let's see how the marks are awarded in this question. First of all, there's a method mark given for using the elastic potential energy, and there is an answer mark given for finding 47.04. Potential energy, there's a method mark for finding potential energy and an accuracy mark for finding the correct potential energy, however you've set that potential energy. And then finally, kinetic energy, there is just a standalone B1 mark if you have identified an expression for that kinetic energy. Moving on, if we've used conservation of energy or attempted to use it, you get M1, making sure that you've put in the three different types of energy. You then get an accuracy mark if you've managed to set up that equation 100% correct with all aspects of it correctly. And then finally, the last accuracy or answer mark is given for having a velocity of 1.87 meters, correct to 2 decimal places. Okay, I hope that all makes sense and that you understood that question.